In this video, I'll talk about some properties of trees, and then we'll prove a couple of them. So first off, one big property of trees is that a graph is a tree if and only if every two vertices of G are connected by a unique path. So there's just one path between every two vertices. That's a nice characterization of trees in terms of paths. Now, a corollary of this is that every non-trivial tree has to contain at least two leaves. We're going to use this corollary. Right, this should kind of remind you about non-separable graphs, or sorry, rather connected graphs all contain at least two vertices that are not cut vertices. It has that sort of similar flavor, but in the case of trees, every tree contains at least two leaves. This is going to be really useful for proving this result, which is that the size of a tree of order n is n minus 1. So this will tell us, exactly what the size of every tree is. We already know paths satisfy this, right? Paths of order n have size n minus 1. And the same is true for all trees. Another property, remember that to be a tree you need to have no cycles and you need to be connected. What this theorem is saying is that if you have a graph of order n and size m, and that graph has no cycles, and it has the right size, that is, that m equals n minus 1, then it has to be a tree. We also know that if G is a graph that's connected and has the right size, then it's necessarily acyclic, and hence it's a tree. And then finally, we'll encounter this theorem, which sort of brings all of those previous theorems together, which says that if a graph satisfies any of these two properties, then it has to be a tree. So connected and acyclic, so G has no cycles, 1 and 2 together, that's the definition of tree. But we also know if G is connected and m is equal to n minus 1, then it has no cycles and it's a tree. And any combination of these two. So if G has no cycles and m equals n minus 1, then G has to be connected, and hence it's a tree. So this is our goal, is to show these properties of trees, and we start by showing that every graph is a tree if and only if every two vertices are connected by a unique path. Now this shouldn't come as too much of a surprise, right? Let's just prove this. Let's just start proving this. So I'll show the forward direction. Suppose G is a tree. Then G is connected. Let U and V be two vertices. Since G is connected, there is a UV path. So here's my U and my V. There's some path connecting these vertices. And if there were another path, so some other path between U and V, and even if U went to one of these vertices, it would produce a cycle. And so the next, right? So what this means is that this path would necessarily have to contain none of those vertices, like it would have to be internally disjoint, but then that would produce a cycle. If there were another path, then this would give a cycle, produce a cycle. So if G is a tree, then any two vertices are connected by a unique path. Now suppose G is a graph such that every two vertices are connected by a unique path. So since any two vertices are connected by a path, it follows that G is connected. And suppose, what I need to show now, right, I need to show G is a tree, so I need to show it's acyclic. Suppose there is a cycle, if there's a cycle, so say containing two vertices U and V, then I have a situation like this. Then there are two UV paths, which contradicts our assumption that any two vertices are connected by a unique path. So G is acyclic. Since it was connected, it's a tree. So that's our first realization of trees. Every two vertices are connected by a unique path. Now, there's a couple observations I want to make about trees here to prove our next result. And that is that in a tree, every vertex of degree 2 or more is a cut vertex. And that follows from this theorem, right? Between any two vertices, there's a unique path. And so if a vertex has degree 2 or more, then it has two neighbors that I can pick. There's a unique path between them, and so every path between them goes through that central vertex, and hence it's a cut vertex. And lastly, every vertex of degree 1, so every leaf, is not a cut vertex. Now, we know that every connected graph contains at least two vertices that are not cut vertices. In a tree, that means those two vertices that are not cut vertices must be degree 1 and hence are leaves. And so those two observations together with that theorem tell us that every non-trivial tree contains at least two leaves. Right, let me say that again, right? Every vertex of degree 2 or more is a cut vertex. Every vertex of degree 1 is a cut vertex. I don't know why I have this parenthesis here. Let me try and summarize that a little bit more clear in case you missed it. Every connected graph contains at least two vertices that are not cut vertices. That was a theorem we proved. Since the only cut vertices, or the only non-cut vertices in a tree are leaves, degree 1, it follows that G has at least two leaves. All right, I'm going to end this video here. In the next video, I'm going to prove theorem 3.13, which establishes the size of every tree. See you there.